I'm Vincent Lauinger from the KIT, and I'm very pleased to introduce you our work about the carrier recovery in coherent optical communications using variational autoencoders. This was a joint work with Fred Buchali from Nokia and Laurent Schmalen. The motivation for this work is the great demand for blind equalizers, where the safe data rate can increase FAC overhead or data throughput. These algorithms have to be flexible and adaptive, and they must support higher order modulation formats and probabilistic constellation shaping. So the state-of-the-art algorithm is the constant modulus algorithm or its derivatives like the multimodulus algorithm. However, the CMA is ill-matched for higher order modulation formats and probabilistic shaping, and the MMA suffers its high implementation complexity and low convergence rate. So actually what we ideally want to use is a maximum likelihood-based receiver, which has been considered, for instance, in GW92. So yeah, let's have a look at our problem, describe our system, and see what we can do. Let's consider now a very general and simple transmission system where we have an input X, which is transmitted through a channel theta, and where we receive Y. So X and Y are realizations of random variable sequences. So we can also look at the corresponding probability densities. So P of X and P of Y, and then given this specific channel theta. So actually we can look at this as a also as a channel estimate, or as a channel estimation problem, where we want to get the maximum likelihood estimation of this likelihood P of Y given theta. What we know is usually the P of X, so the distribution of the transmitted symbols, as well as the P of Y given X and given theta, which is basically the likelihood of the whole transmission system. And this, for instance, we can model well with a circular symmetric normal distribution, where the mean is the convolution of X with the channel impulse response H, and the variance is the noise variance. And in order to compute now the P of Y given theta, so the likelihood of the channel regarding the channel, we would need to sum over all possible input sequences X, which eventually gets intractable. So we need another solution, and one idea, or the idea now, is to use variational inference to solve this problem. And for that, we have to introduce this Q function, which is a parametric function depending on the parameter room phi. And in fact, it's also an approximation of the true a posteriori distribution. So this Q can be seen as a probabilistic decoder, and then the P of Y given X is the corresponding probabilistic encoder. So here we have this variational autoencoder structure. I won't go too deep into maths now. This actually has been considered in CB18 for a very small toy example, which is basically impractical. So let's go a few steps back and derive this in a very general form. And I won't go too deep into math now, but we can rewrite this log likelihood with this expression, where on the right-hand side we have the Kullback-Leibler divergence between the variational approximation and the true a posteriori distribution. And a Kullback-Leibler divergence is a measure of similarity between two densities, and it's always non-negative. So then the term on the left-hand side actually becomes the lower bound. And this lower bound is also called evidence lower bound. So it's a well-known concept in statistics. And this likelihood P of Y given theta, this is also called evidence. So in fact, this elbow serves then as a proxy to maximize the likelihood, and eventually by maximizing the elbow, the Kullback-Leibler divergence becomes zero. So with this concept, we can really approximate maximum likelihood. And this elbow can be now further be rewritten by term A and B, where A tries to shape Q similar to P of X, and B tries to match the equalizer output to the received symbols. So with this concept, we can really build such an ML approximating receiver where phi basically corresponds to the equalizer weights. The Q corresponds to a joint equalization and soft demapping, and can be then used in conjunction with soft FEC. And importantly, this is a blind approach, meaning that we don't need to know the exact transmitted sequence X, but we only need to know the distribution of the transmitted symbols, so the P of X, or we need an approximation of it. So the question is now, how can we build, how can we implement such an ML approximating receiver? And such variational autoencoders are usually implemented using neural networks. So CP18, for instance, they used a convolutional neural network, which then has to do both tasks. So the equalization and the demapping in order to output the Qs. This is potentially capable of compensating nonlinearities. However, no one says that this has to be, or actually this does not have to be ideal for our problem. So basically this scheme is independent of the architecture. So why not using something we know that it works and we know that it's good for our problem? So like a classical butterfly structure with learnable FIR filters, for instance. So this is this linear equalizer block, and then in soft demapper block outputs the Qs. In this way, equalization and demapping are split, and we have access to this X hat, which is basically the equalized constellation. And this enables an easy integration into state-of-the-art DSP chains. As a reference, we then used the very same equalizer block and soft demapper, but the learnable FIR filters are now updated by CMA. And then, of course, we need also a carrier phase estimation block, for instance, a Viterbi algorithm. So, of course, we did some simulations. First, we simulated an AWGN channel with inter-symbol interference, which is caused by the channel impulse response depicted here on the bottom. We simulated the we implemented the CMA and the VAE-based algorithms at an oversampling rate of 2 samples per symbol, and VAE-based algorithms, they are batch-wise. They use a batch-wise update with an ADAM optimizer, and the CMA is implemented based on gradient descent as its common implementation. So it's a symbol-wise update. We also, as a reference, we also implemented DFE and an MMSE, which are both non-blind. So they are supervised, and we also implemented them at 1 sample per symbol. So we see that the VAE-LE is basically approaching the MMSE performance for the whole SNR range, and it also outperforms the VAE-NN, So for the sake of complexity, we for the further simulations, we only considered the VAE-LE, so the linear equalizer version. And in fact, both also outperform the CMA. Then we also looked at probabilistic constellation shaping, and here we see that the CMA, as known, is suffering some penalty, or eventually does not even converge anymore for higher shaping. But the VAE-LE is still able to to approach the MMSE performance. Then we simulated also an optical dual polarization transmission system, so a more practical system where we simulated polarization rotation, PMD, residual chromatic dispersion, and an IQ shift. And here we use an learning rate scheduler. So this is basically halving the learning rate always after a certain amount of iterations, of update iterations. And we see that this scheduler really helps the CMA to converge properly. So the CMA now is approaching the ideal no-easy curve, and also slightly outperforms the VAE-LE for higher SNRs, but the typical working points, basically both algorithms perform similar, also for higher symbol rates. But what's interesting is if we look at the convergence behavior or the convergence, we see that the CMA is converging gradually and slowly as expected, or as we know. And we see also this step-like shape, which is caused by the learning rate scheduler. But on the other hand, the VAE-LE converges in a waterfall-like manner, meaning that it first takes some time, but then it really converges rapidly. And it first converges with one polarization and then drags down the other one. So yeah, this is an interesting characteristic. Of course, we did the simulation as well with probabilistic constellation shaping, and we see similar results to the AWGN channel. So again, the CMA suffers a penalty or even does not converge anymore, while the VAE-LE is really able to approach the ideal no-easy curve, also for higher symbol rates. And now with the learning rate scheduler, it's also able to converge properly for low SNRs and high shaping. So we then did further simulations in order to, within time varying channel, in order to analyze its capability or its resilience towards dynamics. We emulated the time varying channel by a time varying polarization rotation, where we basically have a linear increase with the per update iteration. So this delta phi increases with the x-axis, meaning that here we have high dynamics, and at 0 we have a static channel. Since we analyzed dynamics, of course, we didn't use the learning rate scheduler. So now the VAE is again outperforming the CMA also for a static channel. But more importantly, or more interestingly, we see that we have a quite wide range regarding hyperparameter tuning. So we can either tune the VAE in a way that it has a very high performance at the static channel, but we can also tune it in a way that it's that it's more resilient towards dynamics. And we also introduce introduce something we call flexible or flex update scheme, which is basically a hybrid between batch-wise and symbol-wise update, meaning that it considers some samples for multiple updates. And this, of course, increases computational complexity, but it also boosts learning significantly. So it converges much faster, but also we face a gain for a static channel. But more importantly, it increases significantly the resilience towards dynamics. So it's now capable, or it now converges properly or very good, or now we have less penalty for high dynamics. So this brings me to the end of my talk. So we introduced a novel blind learning paradigm for adaptive equalizers, which is basically architecture independent framework, which outperforms state-of-the-art linear equalizers, especially at higher order QAM formats and probabilistic constellation shaping. And also it has an easy incorporation of PCS formats. Additionally, it incorporates channel estimation as kind of byproduct. So here on the left plot, we see that it approximates the channel impulse response quite well. And on the right plot, we see that it also estimates the SNR within less than 1 dB penalty for the whole SNR range and also for higher symbol rates. So this also enables additional transceiver features. Then I really would like to thank you for your attention, and I'm happy to answer your questions.